environment, it's impractical to train on each task from scratch and in each environment from scratch. And this motivated for me a lot of the work on actually studying how we might leverage previous experience such that we can accelerate the learning of new things. So that's where kind of some of my personal background behind meta-learning came from. But in this talk, I'm also going to talk about kind of our motivation more broadly for studying things like meta-learning. And in particular, I think that there's a bit of a gap between our current paradigm in machine learning research and our current reality in the real world. And this gap is that in machine learning research, we typically take a data set, we train a model on that data set, and then we evaluate that model, or we deploy that model in the world if we're actually doing operations in the real world. However, in reality, the world is constantly changing, and it doesn't make sense to just deploy a static model. So for example, from things like stocks to supply and demand to agents encountering different aspects of the world over time, things are constantly changing. And we want to think about how our machine learning algorithms can be able to adapt to the fact that the world is constantly changing and the fact that these systems will be encountering different things throughout their lifetime. So, okay, we have this gap between deploying static models and the world being changing. How does industry cope? Industry is already deploying models in the real world. Well, we can take it from Chip Huyen on misperceptions of machine learning production. And what she says is that machine learning systems degrade very quickly because of concept drift. And for online machine learning systems, you want to update them as fast as humanly possible. So this seems to actually be a big challenge in real world applications. And it suggests that the way that machine learning techniques are actually being used in industry isn't exactly the way that we develop them for. In machine learning research, we develop them by training a model and then evaluating that model, whereas in reality, these techniques are being used by actually updating them online with the latest data. And so perhaps this suggests that we should actually be thinking a bit more about the kinds of real world situations in which machine learning is being used. So one solution to this problem, of course, is to fine tune the model. And this is probably what Chip was referring to, is you can simply kind of train it on one data set, and then as you get more data coming in, you can continuously fine tune your model on that latest data. And this works quite well. So we've seen in computer vision that you can get substantial gains from fine tuning compared to a random initialized model. In natural language, we've seen a similar trend where as you train from scratch, shown in blue, you get much worse performance than if you start with a pre-trained model, shown in orange and green. And likewise, also in robotics, we've also found that you can actually pre-train a robotic grasping system to grasp at 86% success, and then deploy the model in new situations and fine-tune with a modest amount of data and get substantial gains through fine-tuning. Okay, so fine-tuning seems to work really well, but of course it also has its limits. It requires a non-trivial amount of labeled data in order to adapt to the new situation that the system is in. And so this is in many ways where meta-learning can come in. And in particular, what I'll talk about in this talk is whether we can introduce assumptions that allow us to generalize further with less data compared to things like fine-tuning. And the goal will be to make these assumptions as mild as possible, but also, of course, powerful so that we can generalize far. And a core tool in all of this will be to use meta-learning algorithms. Okay, so I'll be talking about meta-learning for robustness, and as kind of an outline of what I'll talk about, first I'll give a very brief review of meta-learning and what it's currently capable of, and my perspective on the meta-learning problem. I'll keep this brief because I know that many folks are already familiar with this, and Oriel already went through a number of aspects here. Then I'll talk about some of the frontiers of meta-learning, whether we can capture equivariances with meta-learning algorithms in order to generalize further from our training data, and also whether we can use meta-learning to allow us to fine-tune with completely unlabeled data. Okay, but first let's kind of look at meta-learning as a whole. So as an example, a very kind of canonical example that many folks will be familiar with, we often want to solve a few-shot classification problem where we're given one example of 5 different classes. And this is our little training data set. We want to be able to train a model on this data set such that we can generalize to new examples. And the way that we go about doing this is this is essentially what we want to be able to do at test time or at meta test time. And we take image data from other image classes and structure those into training sets and test sets for different tasks, such that when we train a model to adapt on the green box, the training set, it can generalize to the test set in the blue box. Of course, it's important to do this across a number of different training tasks, such that we can ultimately generalize to a new test task. Okay, and this is a very canonical example, but we can really also replace image classification with other machine learning problems, such as regression, language generation, skill learning, in principle, really any machine learning problem. Okay, so that's an example of the problem setup in meta learning. And then one approach for actually solving this is to pass the training data set into a neural network and train this neural network such that when it gets the training set and a new unlabeled example, it can successfully classify this example. This is what Oriel called a model-based approach. I like to call this a black box approach in the sense that we have this black box neural network that is taking as input the training data and using its black box model to learn from that data and make predictions about new examples. And then, of course, another class of approaches called gradient-based or optimization-based approaches, instead of just using a black box neural network, embed an optimization inside this learning process. And this looks something like this, where we have some set of initial parameters, we take our little training data set, then update the neural network parameters with gradient descent or some optimization. And then we get a new neural network, and then we want this neural network to be able to generalize to a new example. We can backpropagate into all of the free parameters of this optimization, such as the initial parameters, the learning rate, and so forth, such that it generalizes with a small number of examples. Okay, so that's a very brief overview of two different classes of approaches in meta learning. Now, what have we seen these meta learning algorithms enable? So of course, I think a lot of people are very familiar with applications such as few-shot image classification, but I'd actually like to highlight here some examples of meta learning algorithms applied beyond few-shot image classification, which I think are some of the actually more interesting problem settings. So one first example of this is we looked at applying meta learning to imitation learning in robotics problems. And the different tasks here corresponded to manipulating different objects. And the algorithm that we used is the mammal model, or an optimization-based model with a learned inner loss function. And what this allowed us to do is give a video of a person. This is just essentially one demonstration or one data point to the robot, adapt to this data using a learned loss function, such that the robot could then actually learn a policy for placing the peach into the red bowl just by watching the video of the person. And of course, this policy can generalize to different positions of the objects, and these are objects that the robot had never seen before. So it was trained on some objects and then tested on these objects. So this is one example. Beyond robotics, people have also actually used this for applications in things like drug discovery, where we want to be able to adapt a model to new molecules. And different tasks here correspond to predicting the properties and activities of different molecules. They studied different optimization-based meta learners, including mammal, first-order mammal, and almost no inner loop. And what they found here is that meta learning algorithms were able to perform significantly better than simply fine-tuning models from the pre-trained initialization. Another example, also kind of from a medical setting, is studying whether models could be adapted to new diseases. This is a paper from 2019 that looked at whether you can classify different skin conditions with a small amount of data. And this is a problem that's really important because with different diseases, some diseases are a lot more rare than others. You have essentially this very long tail of skin conditions. We want to be able to meta learn such that if we take the data from the head of this distribution, we can actually use that to effectively generalize better to the conditions for which we have a very small amount of data. And so they took something similar to prototypical networks, adapted that to use multiple prototypes per class and incorporate unlabeled data, and found that they were able to outperform something like k-nearest neighbors on pre-trained features, and also they're able to roughly match the performance of fine-tuning, but without requiring any extensive retraining on the data. Okay, so those are a few examples. A couple more examples. We've looked at settings in another setting in robotics where we want to adapt to different terrains. And we can then, after meta training on different terrains, we can actually adapt online to a missing leg, and the robot can learn how to walk in a straight line, even though it's actually missing its front right leg here. And lastly, people have looked at adapting to settings where you have different regions of the world, where the goal is to classify the land covering from a satellite image. And they use an algorithm like MAML to essentially adapt to different regions of the world, such that if you're in a new region and you don't have a lot of labeled data, you can effectively train a model for that region of the world. Okay, so that was maybe a very quick overview of some settings where meta learning has been applied. But I think that it actually is really nice to look at this more broadly, because it shows us what a task can mean in different situations, and it really shows us the breadth of problems that these algorithms can be applied to. And I also hope to see kind of more meta learning works evaluate on these kinds of problems in the future, because I think that they are, they have real world implications, and they also may present challenges that are a little bit different from the standard settings like mini ImageNet and OmniGlot and so forth. Okay, so beyond the state of meta learning, now I want to talk a bit about some of the frontiers of meta learning and whether we can leverage meta learning to robustly adapt to changing situations. And the motivation for this next piece of work is that I mentioned fine-tuning as one solution to distribution shift, but another solution to distribution shift is actually to build in structure or build in inductive biases to solve the problem. And one particular kind of structure that has been very successful has been something like convolutions, which builds in translational equivariance into the model in order to essentially allow it to generalize to shifts of the data. And this is great when we know what the structure is and when we know how to build it in, for example, things like convolutions. But there are a lot of situations where we don't know the structure and we don't know how exactly to build it into the model. And so what we wanted to answer is we want to study whether we could discover equivariant and invariant structures via meta learning, if we can kind of recover things like convolutions from data that has that structure, such that when we then take those models and deploy them to new settings, they can also generalize further by building in those symmetries into the model. So now you might ask, well, do meta learning algorithms already do this? We know that meta learning algorithms are capable of recovering some amount of structure, but do they already build in things like equivariances and invariances? So to look at this, we can look at the structure of an algorithm like MAML, and we get this diagram that I showed previously. And we know that MAML can learn equivariant initial features. So MAML just learns the initialization of the network. And it could be that it learns initial features, initial parameters that capture some amount of equivariance. However, if we're just running gradient descent from those initial parameters, we don't know if that equivariance will be preserved throughout the optimization, because the optimization isn't doing anything to, it's allowed to do whatever it wants. It isn't necessarily constrained to preserve any of that structure. So this equivariance may not be preserved through the gradient update in MAML. And so our goal in this work was to try to figure out if we can decompose the weights into the equivariant structure and the corresponding parameters, such that in the inner loop, we only change the corresponding parameters. We try to preserve that equivariant structure to make this learning more efficient and to generalize better. And if we can do this, we essentially only update the parameters in the inner loop and retain the equivariance in the inner loop. And then in the outer loop of the meta learning process, we're going to update both the initial parameters as well as the equivariant structure. Okay, so how do we actually go about doing something like this? To think about this, we can look at how equivariances are represented in neural networks, and we can look at an example. So let's take the example of convolutions. And convolutions, like a 1D convolution will correspond to something like this, where you take a filter and you slide that across the input to produce the output y. And it turns out that you can represent this convolution function also as a fully connected layer. It's essentially kind of a special case of a linear function. And the way that you could represent a 1D convolution as a fully connected layer looks like this matrix on the right, where you essentially copy the filter parameters across the diagonal of the weight matrix. So this is one example of how kind of an equivariance can be represented in a fully connected layer. And building on this example a bit more, if we wanted to actually go about learning something like convolutions, what we could do is we could decompose this weight matrix into two parts. We can essentially reparameterize it into the underlying filter parameters A, B, and C, and a separate matrix that tells us how those underlying parameters will be used in each of the entries of our fully connected matrix. And if we take the product of this, the sharing matrix and the vector of filter parameters, we'll get a vector, of course, and then we can reshape this vector to form the fully connected matrix that's represented on the left. So this can represent things like convolutions, where the sharing pattern encodes essentially the translational equivariance and the underlying filter parameters encode the filters of the convolution, where essentially U captures the symmetries and V captures the underlying shared parameters. And it turns out theoretically, you can use this to represent things like convolutions, but you can also, theoretically, this can directly represent a decoupled equivariant sharing it can represent a decoupled equivariant sharing pattern and filter parameters, not just for kind of standard convolutions, but for all group convolutions with finite groups G. And this is very useful to know because kind of the class of group convolutions covers much more than just convolutions. It includes symmetries like reflection, like translation, like rotation, and so forth. Okay, and so now that we have this form of a reparameterized weight matrix, what we can do is with meta learning, we can learn this sharing matrix U and adapt the underlying shared parameters V. So what we'll do is in the inner loop, we'll only update the parameters V, keeping the equivariance fixed. And in the outer loop, we're going to learn both the equivariant structure and the initial parameters V. And so what this looks like visually is the inner loop is shown in the top row, where our inner loop loss is going to be backpropagated into the weight matrix and into the underlying parameters V. And then after this adaptation, we're only going to have updated V to V prime. U is going to be fixed. And we're going to evaluate the model with these updated weight matrices where only V has been changed. Okay. And now one important assumption that I'll note here is this is assuming that you have a set of tasks and the set of tasks shares some common set of symmetries. And if it shares that common set of symmetries, then that should be reflected in kind of our goal is to recover those symmetries that are shared by all of the tasks in the U matrix. Okay, so we refer to this as meta learning symmetries by reparameterization, or MSR. And now let's get to the experiments. So our first question is that we want to ask is whether we could recover convolutions from translationally equivariant data. To answer this question, we built synthetic data that was just random 1D convolution functions, and we meta-trained across all of those random 1D convolution functions. And what we're looking at here is we measured mean squared error when looking at a new 1D convolution function. And we compared mammal with a fully connected layer, mammal with locally connected layers, and mammal with convolutions to MSR that's trying to reparameterize a fully connected layer. And what we find is that first, MSR is able to match the performance of mammal with convolutions, suggesting that it's able to recover something that is as performant as convolutions when looking at translationally equivariant data. And second, if we actually visualize the recovered weight matrix that MSR learns, we see that it exactly recovers the translationally equivariant structure that I mentioned before. It's able to recover the 1D convolutions. Okay, so now that we've seen that we can recover convolutions from translationally equivariant data, can we recover something better than convolutions? And in particular, if we looked at data with partial translation symmetry, so we can look at data that has, in this case, we looked at essentially different locally connected functions with different ranks. So a rank of 1 means that there's one filter that's shared for all of the locally connected filters that corresponds directly to convolutions. But with k equals 2 and k equals 5, we only have partial translation symmetry. And so in these cases, mammal with convolutions is specifying too much equivariance, and so it doesn't perform as well as it could. And we find that MSR, by reparameterizing a fully connected matrix, is able to actually recover the underlying partial translation symmetry and do substantially better than mammal with kind of a misspecified symmetry. And then lastly, we looked at data with translation, rotation, and reflection symmetry, and started with MSR actually on top of a convolution layer. And we find that it's able to perform well by nature of recovering the rotation and reflection symmetry, whereas mammal with convolutions isn't able to effectively recover that structure. Okay, and then lastly, we also looked at augmented data to try to understand if we can essentially try to take augmented data and bake that data augmentation into the architecture. And so the way that we did this is we took our kind of typical support query set and then augmented only the query set or only the validation set and kept the train set unaugmented. And the goal here was to develop an architecture such that it can adapt to the unaugmented training data and generalize to augmented data. And what we found here is that MSR was able to essentially recover an architecture that essentially builds in that augmentation into it. And it was able to perform substantially better than mammal, and also better than mammal with a larger network that has the same number of parameters as MSR. It also does substantially better than almost no inner loop, which is interesting because ANL can essentially learn equivariant features and then learn something on top of that. And then also it performs comparably to prototypical networks in the omniglot setting, but is able to do better in looking at augmentations with mini ImageNet. Okay, so to conclude this part, one of the things that I find interesting about this is not only that we can recover invariances and equivariances from data, from a set of tasks, but that also this essentially provides a framework for thinking about the interplay of features and structure in meta learning, where essentially we want to recover the structure and keep that fixed in the inner loop and only change the features in the inner loop. Okay, so capturing equivariance is one way to allow us to generalize further to data that has essentially these sorts of symmetries. The last thing that I'd like to talk about is whether we can adapt to new situations without any labeled data. And the particular kinds of distribution shifts and tasks that we're going to be looking at are group shifts. And in particular, what this means is we're going to assume that there's this categorical group variable z. And this could be something like different users, different locations, different times of day. And it can often be derived from metadata. And then we're going to assume that our training data comes from a distribution over the group times a distribution of xy given the group. And the test data comes from the same exact distribution, except there's now kind of shift in the distribution over the group. So we now have this p-test over z that's different from the training distribution. And this sort of distribution shift can capture things like label shift, most forms of covariate shift, and it also captures problems like federated learning, where different z's correspond to different users, and the users that you're seeing at test time are different from the users that you were seeing during training. Now, it's worth mentioning that there are kind of prior approaches to handling this sort of distribution shift to different groups. So one very nice framework for this that has a lot of kind of nice theoretical principles is the idea of group distributionally robust optimization. And the way that people try to use this approach to solve this form of distribution shift is to form an adversarial distribution over your group Z, and then to optimize over the worst case group at the worst case group during training. So instead of just taking your expectation over your training group, you're actually going to be taking the soup over your group, and you're going to be minimizing for this the loss under that worst group. And this is great in that it can enable robust solutions, because if you're going to be seeing different groups at test time, being pessimistic and choosing optimizing for the worst case group will prepare you for those kinds of test groups. And it's also less pessimistic than things like adversarial robustness, because your uncertainty set over these groups is very structured. The downside of these approaches is that they often sacrifice average or empirical group performance in favor of robust performance. So what we're going to try to do instead is, instead of trying to be robust to the group that we're seeing during training, we're going to try to be able to adapt to different groups. And we want to be able to adapt, as I mentioned, with unlabeled data. So as a concrete example, say that we want to adapt to different users' handwriting. What we want to be able to do is take a batch of unlabeled data from a new user at test time and be able to adapt our model using the unlabeled data from that user. And so we're going to take this unlabeled data, adapt our model with some process, and then label the data from that particular user. And this allows us to essentially adapt models to different users or different parts of the distribution. And this does make one important assumption, which is that the test inputs from one group, such as one user, are going to be available together either in a batch or streaming at test time, rather than being intermixed. So we're going to refer to this as adaptive risk minimization, where we want to essentially be able to not just minimize empirical risk, but minimize the risk after this unsupervised adaptation procedure. And the way that we can prepare models for this sort of unlabeled adaptation is during training to construct subdistributions of the training data and train for adaptation to these different subdistributions. This is very similar to a standard meta-learning setup. The main difference is that we want to be able to adapt with unlabeled data. However, it's pretty nice that we can actually pretty simply take existing meta-learning algorithms and change them a little bit to be able to handle unlabeled data. So for optimization-based meta-learning algorithms, you need to actually evaluate a loss function in order to adapt. So you can actually learn a loss function, L, such that when you take gradients on that loss function with unlabeled data, you get good performance. This allows us to adapt to unlabeled data. You can also take black box approaches and pass the unlabeled data into those black box approaches and train it such that it can effectively make new predictions given that unlabeled data. And actually one really simple setting here that you can actually, that's actually quite nice, is you can actually, instead of taking like an LSTM black box approach, you can actually compute some context where essentially the unlabeled data is coming in through the batch norm statistics. So you take your unlabeled data, you compute batch norm statistics across that batch of unlabeled data, and use those statistics when making predictions on examples from that group. And this is a very simple way to incorporate information from the unlabeled examples. And it's a little bit different from the standard batch norm, because in standard batch norm, typically you want your batches to be uncorrelated. And here you're actually purposely making them correlated and also making them correlated at test time so that you can actually leverage information from that batch. Okay. So that's kind of the overarching framework where we want to adapt a distribution shift with unlabeled data. And to provide kind of one simple example of why adaptation makes sense, we can look at a really simple 2D case. So say that we we had a 2D classification problem, and one of our groups was shown here in red, another group is shown in blue. And then at test time, we get some new inputs that look like this. And our goal is to classify these inputs. Just by looking at the unlabeled data, it's pretty easy to figure out where the decision boundary should be. It should be right here, where everything on the top right is positive and everything on the bottom left is a negative or a circle. And this is only possible because we're actually adapting our classifier and looking at the unlabeled data. If we instead try to train a single model to be able to be robust to these different distributions, it actually wouldn't be possible to perform well. So things like empirical risk minimization, as well as robustness approaches like DRO and invariance approaches, would still try to learn a single decision boundary, which wouldn't be able to effectively separate out the data. And so this is kind of an example of a kind of problem where adaptation is really important and we're able to adapt with completely unlabeled data. As another quick example, there's also something in statistics called Simpsons Paradox. And what it says is that essentially if you look at the data as an entire population, sometimes the trend is very different than if you look at individual subpopulations of the data. And so we can see this where essentially the individual groups have a positive slope, whereas if you look at the population as a whole, the correct model would be something that has a negative slope. So the model is completely different if you're actually trying to adapt versus if you're trying to learn a single model for everything. And you can be much more accurate when you actually try to adapt to these groups if you actually have, in problems where you have these kinds of different groups that you can adapt to. Okay. Cool. So experimentally, we looked at trying actually applying these methods and adapting with unlabeled data to different scenarios, and we compared to standard empirical risk minimization, distributional robustness, as well as a baseline that upweights all of the groups to the uniform distribution. And we compared all of these three methods to a method that adapts with unlabeled data, that either adapts with some sort of context variable, that adapts using the Bostrom statistics, or that adapts with a mammal-like method with a learned loss function. And so if we took the federated extended MNIST benchmark, which is a problem studied in the federated learning literature, where the goal is to adapt to new users at test time with only unlabeled data from that user. We also compared to a federated learning method as well. And on this benchmark, we found that we were able to get a 5% improvement in average accuracy on these characters, and also get a 10% improvement in worst case accuracy with regard to the worst user. And this metric is important because we often don't care about just the performance of the users in aggregate. If some users are having a great experience and some users are having a really terrible experience, then that's also not great for your business, for example. So essentially by adapting to unlabeled data, we can do substantially better. And as a qualitative example that shows what it's doing, say we wanted to classify this image here from a user. ERM would tell you that this is a 2. And if you only looked at this image, it's quite reasonable to think that it's a 2. However, if you look at the images from this particular user as a whole, if you only look at the 2 images in the black box, it also makes sense to predict it as a 2. However, if you looked at all of these images, you'd actually realize that it's an A, because in the top right, you can actually see an example that looks like a 2 written in a different way, which suggests to you that the user writes 2s in a different way and writes A's with this particular style. So this is an example where actually leveraging unlabeled data can allow you to adapt much more effectively to these examples. And then lastly, we also looked at an experiment where we wanted to adapt to different kinds of image corruptions. And so we trained the model to adapt to different image corruptions during training, and then at test time, it's given images with new image corruptions, and it needs to be able to predict the corresponding image class. We trained using 56 corruptions and tested using 22 disjoint corruptions. And on CFAR 10C and Tiny ImageNet-C, we were able to see a 3 to 10% improvement in average accuracy and 8 to 21% improvement in worst case accuracy, which is pretty substantial. And again, this is only using unlabeled data, a batch of unlabeled data at test time. Okay, so to conclude, today I talked about how there's this gap between our current paradigm and our current reality, where we typically think about evaluating static models, where in reality, the world is constantly changing. I talked to how meta-learning can be a tool for allowing models to adapt quickly with labeled data to these changing circumstances, such as changing objects, molecules, regions, and conditions over time. I also talked about how we have some preliminary evidence that meta-learning can be used to capture equivariances by reparametrizing the weight matrix, which can allow us to adapt more robustly by capturing the symmetries that exist in the world. And lastly, I showed how we can use meta-learning to adapt to new situations with completely unlabeled data with adaptive risk minimization. I'd like to thank my students, especially the students who were involved extensively in this work, including Alan, Tom, Marvin, Henrik, and Nikita, and also Sergey, who's a collaborator. If you're interested in learning more about meta-learning, I teach a course on meta-learning at Stanford, and all of the lecture videos and slides are available online. And also, if you're interested in distribution shift more broadly, we actually put together recently a benchmark with distribution shifts that arise in real world applications and for which current methods actually struggle significantly. So I'd encourage you to check that out if you're interested. And I'd be happy to take questions. Thank you.
Thanks a lot, Chelsea, for the excellent talk. Do we have any questions from the audience?
Hi, I have a quick question. Thanks for the talk, pretty interesting.
Open your camera when you're—
Yes, if you can give me 1 second. Here, hopefully you can see me now. Hi. I have a question which might not be exactly about what you spoke, but it's still on meta-learning.